Welcome. In this video I'm going to show you how you can analyze a single scale variable using R and my stikpetR library. I'm using Jupyter Lab with an R kernel that's running R version 4.3, but this should work in any IDE that can handle R, so for example also R Studio. To analyze one, what I'll be doing is I'll create a bin frequency table to get an impression of the data. Then use a histogram to visualize that data. Get the mean and standard deviation, and that concludes a little bit about what I can learn from my sample. Then I'll use a one sample student t-test to test if the mean might be a specific value in the population, and as an effect size measure to go with that test, Cohen's d for one sample. Those were just some choices because there are alternatives like a box plot or a stem and leaf plot for your visualization. All kinds of different measures that can be done. A test, we have two alternatives, so one sample Z test or trim mean or Juan test, and two different effect sizes that could have also been used. I have separate documentations for all the functions and also separate videos if you want to learn more about any of them. This video will be simply mostly a quick rundown on how it could be done. My stikpetR is not available directly on CRAN, so you'll have to get it from my GitHub account, and once you've installed it, you can load it just as any other library. Now the example I'll be using is from the General Social Survey data from 2012, adjusted for some example purposes. I won't actually need all of its data, I just need one numeric field, so I'm going to be using age for that. However, this isn't fully numeric. There is an 89 or older category in there. So I'm just going to replace those with 89. So I really have some numeric data. And just to be sure, I make this as numeric. So it's really numbers, so a scale variable. As mentioned earlier, the first thing I would need is a frequency table. So I'll run my tab frequency bins. That's in the stikpetR. It gives me the lower bound and upper bound of the bins. As you can see, they're always having a bin width of 6, so 84 plus 6 equals 90, 78 plus 6, 84, etc. Which makes the frequency densities a bit redundant. These are more relevant if you have different bin widths. You can actually set the bins in this function, so if you're interested in that, have a look at the details for that function. Looking at this, it seems to be going up and then settle around the 200, and then after 54 it starts to go down again. As mentioned earlier, we might want to visualize this, so I'm simply going to be using visualize histogram, and now I get a nice histogram of the data, and indeed, although there's a little additional drop around here, it starts to drop quite a lot. As measures of central tendency, let's do the mean. So the average age was 48 years old. You can also do the median if you like, or the mode, or some other types of mean. But the arithmetic mean, which this one is fully called, is the most standard one. And that's usually accompanied with the standard deviation, the unbiased sample standard deviation, which apparently is 17.68. This is a rough indication of the average distance to the mean, although that would be a different measure of variation. It's actually the square root of the average squared difference with the mean. But most scores will be between that 48 and then plus minus 18 if you round this. Now, I'm going to test if the average age in the population might be 50, so I'm going to be using a student t-test. I'm going to set my hypothesized mean to 50 and look at the results. So hypothesized mean, the sample mean again, the t statistic, the degrees of freedom, which is simply the sample size minus 1, and the most important one is this one, the p-value. If this is below a predefined threshold, usually 0.05, we would speak of a significant result. This e minus 0.6 means we need to divide this by 10 to the power of 6. So that's going to be a 0 point, and then I think it's 6 or 5 zeros and then 6. So it's really, really small. So far below the usual threshold of 0.05. So we would say, well, in the population, the mean is most likely significantly different from 50. Is it a lot or just a little bit different from 50? For that we could use Cohen's d, an effect size measure. Again, there's a function for that, and in this case it's 0 minus 0.10. We can actually convert this to a regular Cohen's d, because this one is specifically for one sample, by using the ES_convert function. That gives us the regular Cohen's d, and for those there's a function th_Cohen_d, which is actually the rules of thumb for Cohen's d. Some will frown upon using these kinds of rules of thumb. You should talk to experts in your fields, but otherwise, according to Savilovsky, this can be classified as very small. So even though it's significantly different from 50, it's probably not going to be much different from 50. As we saw already in the sample, the average was 48, so it's not going to be like 12 most likely. If you're interested in the alternatives, I'll quickly run over them. The box plot is available as a function. A stem and leaf display, in this case though, with so many data points, it's not going to look nice. Here's actually the stem and leaf display itself. You need a really large screen or reduce the font size to actually see it. It does also return a data frame with the stems and the leaves. Alternative measures, there are all kinds of different means, winterized, trimmed, Olympic, etc. They're all available under MA mean, and then simply set the version. So here's a rundown of all of them. Quartiles, there are actually a lot of different ways to calculate these, but the default is used here. Quantile, same thing, let's use 10 of them, so we have actually 10 values now, or 11 if I'm not mistaken. Different measures of variation that you could actually use are under that ME measures variation. Quartile ranges like interquartile range, semi-interquartile range, all available for you. Alternative tests, the one sample Z test if you don't want to use a t-test, which with large sample sizes will be very similar to the t-test, or the trimmed mean, or sometimes known as a Juan test, is also available. Alternative effect sizes, hedges G, can be used, and last but not least, you could actually also use the common language one, which is in this case 0.38. There are also then some rules of thumbs that can be used for these, but we'll see the separate videos on those if you're interested. Alright, I hope this video was helpful, and thank you for watching.